Hi, in my previous video I went through what is required to solve a pair of simultaneous equations involving two or three variables, and it was concluded that in terms of matrices, the determinant of the coefficient matrix plays a large part in knowing whether or not a solution exists. In this video, which is the second of a three-part set, we're going to look at how we can use matrix operations to solve a pair of simultaneous equations involving two variables. So here's an example. We have our simultaneous equations, x plus y equals 7 and 3x minus y equals 1, and graphically they represent two straight lines with the intersection, which is the solution to the simultaneous equations x equals 2 and y equals 5. But how can we solve them using matrix operations? As mentioned, the determinant of the matrix plays a part, as well as what we call the inverse of the matrix. And to be able to do that, we have to know how to multiply matrices. So we can start by looking at two matrices, let's call them A and B, and matrix A will be of order A by B. A times B really means the order of the matrix. That means it has A rows and B columns. And matrix B is of order B times D. That means it has B rows and D columns. Notice that for the matrix multiplication to occur, to be valid, to be possible, the columns of the first matrix A has to be the same number as the number of rows of matrix B. Otherwise, multiplication is not possible. And once we know the order of each matrix, then the matrix product, A times B, will be of order A times D. That means it will have A rows and D columns. The process we follow to multiply A with B is to multiply the rows of A with the columns in B. So let's try one. Here we have our two matrices, A and B. Matrix A is of order 2 by 2. That means it has 2 rows and 2 columns. And matrix B has 2 rows and 1 column. That means the solution will have 2 rows and 1 column. So we begin with taking the first row of matrix A and the column of matrix B to multiply the numbers, the elements in each row and column. That's the order we follow. 2 times 4 plus 3 times 7, and that equals 29. So that's our first part of the answer. Then we move to the second row of matrix A and we multiply that with the column in B, and that gives us, as you can see there, an answer of 39. What about this one? Matrix A is a 2 by 2, matrix B is a 2 by 2. So the answer will have 2 rows and 2 columns. We're going to work out the 4 elements that are in the matrix product, shown there with 4 X's. Okay, so we start with the first row and the first column. First row of A, first column of B, like that, and multiply to give us an answer of -4. Then the first row of A with the second column of B to give an answer of 12. Then the second row of A with the first column of B to give -1. And finally, second row of A with the second column of B to give 17. If we look at these two matrices A and B to work out the product, we will notice something interesting. If we follow the process of the previous example, the matrix product will give us a 2 by 2 matrix, and look at the elements, the numbers in the solution. The diagonal, the leading diagonal from top left to bottom right, consists of 1s and the other 2 are 0s. That is called the identity matrix, and it will be useful when we're working out the solution to our simultaneous equations. So we can write that the matrix product, A times B, for these two matrices is equal to I, the identity matrix. Because of that property, we say that B is the inverse of A. Think of the identity matrix as having an equivalent in the normal number system as 1. In other words, a number times another number equals 1. That means one number is the reciprocal inverse of the other. For example, 4 times a quarter equals 1. So quarter is the reciprocal inverse of 4. And that's how we write it. B being the inverse of A, we can write B equals A inverse, or A to the minus 1. Or we can equally write A equals B to the minus 1. And that means, of course, that the product of A with its inverse, A to the minus 1, is the identity matrix. Alright, let's try the product of these two matrices, A and B. Just writing it down. So we have a half in front. Then we can work out the matrix product of the two matrices, like that. And we can take a half of each of the numbers, each of the elements in that matrix, 2, 0, 0, 2, which gives us the identity matrix that we spoke of. So that means that A and B are inverses of each other. So now that we can recognise a matrix and its inverse, the question remains, because we need to know this, how do we find the inverse of a matrix? One method is to use algebra, and we'll do that just to show you where the end result comes from. Let's suppose we write matrix A as consisting of the numbers A, B, C, D, and let's suppose its inverse will consist of the numbers capital A, B, C, D. What we want to do is to work out the relationship between the capital letters and the lowercase letters. Now, we know that a matrix multiplied with its inverse is the identity matrix, so we can substitute for A and its inverse to give us what we have there. And now, carrying out matrix multiplication, that's what we obtain. And from that, we can compare the elements that are in the same position. For example, little a times A plus little b times C has to equal 1 because they are in the same position, and little a times B plus little b times D has to equal 0, and so on. And we obtain 4 equations involving those unknown values A, B, C and D. Now, is there a way of working out the values capital A, capital B, capital C, capital D in terms of the lowercase values A, B, C and D that we are given? What we can do is choose any pair of equations and eliminate one of the capital letters. I've chosen equations 1 and 3, and I will be eliminating capital C. And to do that, I've multiplied equation 1 by D, as you can see there. That's what that is saying. And I've multiplied equation 3 by B. So the first equation becomes what you can see there. The third equation gives you what you can see there. So we have those two equations. Notice that the coefficients of capital C are now the same. So by subtracting one equation from the other, we can eliminate capital C. And to do that, we can subtract equation 3 from equation 1. And just with a bit of manipulation, we can take out a factor of capital A. And then to get capital A on its own, divide both sides by AD minus BC. So we've got an expression for the first element of the inverse in terms of the constants A, B, C and D. We can do the similar thing with another pair of equations, and by doing that we can obtain the 3 other relationships for capital B, C and D. There they are. If you've watched the previous video, you might notice something about the denominator in each one. AD minus BC, if you notice, appears in each expression. That is the determinant of matrix A. So we can write the inverse, which is capital A, B, C and D, and we can replace each of those with its equivalent expression, like that. And taking out a common factor of AD minus BC, we have our expression for the inverse matrix A. And replacing AD minus BC by knowing that that is the determinant of A, there's our final expression for the inverse A, which is that it will be 1 divided by its determinant times the matrix with elements DA, negative B, negative C. Do you notice how we obtain these the fast way? The A and the D of the original matrix have interchanged, and B and C have become the negative. Now let's apply what we've learnt to solve our pair of simultaneous equations involving two variables. Let's suppose these are the two equations. We will use the values a1, b1, c1, a2, b2 and c2 to represent the constants we are given. And writing that pair of equations in matrix form, we obtain what you can see there. Now what we want to end up with is something that looks like xy equals some value for capital X and some value for capital Y. So that means we must find a way of replacing that coefficient matrix that will cancel with it. And this is where the inverse comes in. The inverse of that coefficient matrix is what you can see there. So if we pre-multiply both sides by the inverse of the matrix, that's what we obtain, the one shown in red. And what we have here on the left, there's our inverse matrix, and there's our matrix A. And of course we know that the product of the matrix with its inverse gives us the identity matrix, and there it is. We can replace it with the identity matrix, and we still have what is shown on the right. So the identity matrix multiplied by matrix xy just gives us xy. You can check that out by multiplying rows with columns. And there's our solution for x and y. We can of course expand the matrix product here, but we will do that using numbers. Alright, let's apply that with actual values. First of all, write the simultaneous equations in matrix form. Find the determinant of A, which is 14. Work out the inverse of A, which is 1 over 14 times the matrix there. Now pre-multiply our original matrix by the inverse of matrix A. And of course we can replace all of that by the identity matrix, like that. And on the left that becomes xy. And if we perform the matrix multiplication on the right hand side, we obtain matrix 14, 28. And the 1 over 14 means of course we can divide each of the numbers 14 and 28 by 14. And that gives us a final value of x equals 1, y equals 2. Graphically, geometrically, this is what's happening. The two equations are the two straight lines, and the solution that we have found, 1 and 2, is the point of intersection. X equals 1, y equals 2. Okay, so we found how to solve simultaneous equations involving two variables using matrix methods. In the next video, we go on to the next level to solve a system of three equations involving three variables using matrix methods. A bit more challenging. So, see you in the next video. Until then, bye-bye.